Hello, welcome to episode 23. We need to generate our tables today. So the way we're going to do that is we're going to take a look at this keyword layout struct. We're going to figure out what parts of this need to go out into the table. You probably have to do some lookups into the tokens table now. We're going to figure out what data structure we need here. We have to, figure out how we're naming things. There's a number of concerns we have to address. And essentially what we're doing is we're just plopping out these hash tables into some straight up C arrays so that they can be used by other parts of the generated code, right? The Lexer code themselves is going to look into these tables when they're doing an emit. So let's get these keyword tables started up. So a first rough draft is going to look like this. We're going to want something like our hash array or something like that, and that's going to look like this. Excuse me. We know exactly how many elements are going to be in the hash array. So the problem that I guess I need to address first and foremost is when I'm hashing these things, if I'm going to make a hash array, the point of the hash array is that it always contains the hash of the thing I stored at a particular slot so that I can just do hash comparisons first before doing full string comparisons. But I guess that means that I kind of want to adjust my hash function in a certain way. In particular, I probably want my hash function to never emit a 0 as its hash value. And so for that to be possible, I would need to either say if I get a 0, emit a different hash value. If that happens, then whatever hash value I get would be twice as likely as every other hash value, which is a bit of a wrinkle in the system. I could adjust my hash function to make it impossible for it to output hash values of 0 while still being possible to output everything else. Or I could just say that, okay, my hashes, whenever I put them in the table, the hash value I store in the table always has one of its bits set to 1, even if the real hash doesn't have it. So you're actually getting 63 bits, even though you're getting 64 bits of hash collision resolution. You're only getting 63 bits of checksumming or something like that, right? To avoid the direct checks. That's kind of an attractive option to me. So basically, the hashes themselves don't have the bit set to 1 necessarily, and hashes can have a 0 in them. But when I go to do the comparisons, I just have to say, hey, before we do a comparison, take both of these, add the first bit, add bit 0 to have be a 1 in either case. Whatever it was originally, ignore it, make it a bit 1, and then if these hashes are equal, in that case, then you do the string comparison. What that will mean is that it's possible for two keywords, even if they don't have the same so I would just have to make sure that as I'm generating this, that I check to see if the keywords or if the hashes that I have are non-colliding with that as their comparison function, right? Where the comparison function doesn't compare the first bit or something like that. Yeah. Then I could still get the optimization I thought of a couple episodes ago where we don't have to do more than one string comparison inside the table. We'd still have to add that as part of the layout logic for the keyword tables as well. So that's just an optimization that I'll put off for now. For now, we'll just do however many string comparisons it takes to get the correct behavior, and we'll live with whatever we get. So first things first, let me stick in some numbers here. We know that our slot count is returned right here, so we can do that. What are you complaining about? Yeah, so you want the keyword count as well, I guess. Which makes sense. So there we go. We're getting tables of size 77, 15, and 1, which is good. If we run this again, we'll get different results sometimes. Looks like the 15 doesn't change as often as the 70, or at all. I probably kind of fine-tuned this for the 66 case that I was looking at, but that is the most expensive one I have in my set. Right, so it's likely that this thing here is always finding that it can do its job with just 15 slots, which kind of makes me wonder how many slots it has filled, which we'll find out when we do the next step, which goes like this. Let's do it like this. I in the key layout dot slot count for each slot. If the key layout slots I equals 0, else, then if it equals 0, we output a 0 comma, right? And I'm going to have, since these are all 64-bit integers, I'm going to have all of my numbers output as 3, 4, 5, 6, 7, 8, full width values like that. So another way I could do this is say, look, I want a %, 0, let's see, 2 is a byte, 4 is a short, 8, 16, right? So I want 16 hex, and then 0 is the number. And here, it's the same thing, except the number is going to be the hash that we got there. So we didn't actually store that in the keyword layout already, but we can easily fix that. Hashes, right? So here are our slots. Here are our hashes, and that's just another array of U64s. Whenever we insert something into one of these spots, we just need to do the following things. We need to say the layout.hashes index equals the hash we've already computed, and whenever we're doing a swap, we need to make sure that we swap the current hash that we have with the hash that is sitting there in the array, right? There we go. And now I can do key layout.hashes I or 1, right? So that should give me, cool. Alright, so now we're getting these hashes here. Some interesting notes. My hashes aren't using the full... I bet that this is losing precision somewhere along the way. We don't lose precision. There we go. So that's good. All of these have their first bit set to 1. Again, if I took that out, that is actually not the real hashes. Rather, these are the hashes I'm going to use for comparison. So now you can see that some of them are even numbers here. We have A's, we have a 0, we have a 4. Probably have, you know, other things in here if I spend enough time staring. I think C is even, 8 is definitely even, 6 is even, etc. But point is, we don't want those. It's kind of funny how this means that tables are different every time. I love that fact. It's just so funny to me. So here we have that. Here we can see that this is actually a completely full table. So it must be that it manages to get this table down to a point where it doesn't, like, the amount of optimization effort it has, it just doesn't even need to put in any blank spots in this table to find one that meets the threshold. So that means it must be trying to store 15 things in here, and successfully doing it in 15 slots every single time, which is pretty cool, I think, because it's not even using heavy optimization effort to achieve this. So this is like, I don't know, this is like, since it's going for, I think it's going for 2/3, right? Yeah. Yeah, I'd be curious to see what the error is on that real quick. I'm just so curious. But we're not going to go down that road again. This is definitely going to be good enough. If its optimization error is clearly within 1 per slot, right? On average. So, really cool. So next, what we want to do is we have the array of hashes. We need to stick in the array of keys. So let's sketch that out. All of this is getting sketched out, and we'll have to do a second pass over every part of it for reasons that will make sense soon. So for keys, what we're going to do is we're probably going to use my built-in string type, because that lets us use a pointer and a size. And then for each key, what we need to do is, if it's a null key, then we're going to output 0, 0 as the key and be done with it, right? And I'm probably going to put a new line after every key in this case, so we don't need this. And if it's not a null key, then what we're going to output is going to be the following. We need an exact recreation of the string. So this is another case where do I want to have to escape that? Absolutely not. I don't want to have to escape that. So we're going to use a variable instead. That variable is going to be key underscore array underscore %d. And then the size of that can just be an LLU right here. %d will come from I directly, and the LLU will come from what am I thinking? Slots lexeme size, right? Yep, that works. So here we go. So what is this key array underscore 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 19, 20, 21, 23, 25? What are those? I just made those up. What are they actually, right? Well, they're going to have to be U8 pointers. And so what we're going to have to do is, before we do this, 5-second interruption. So, before we do that, we're going to need to create each of those as things. So if we have a real slot here, we're going to fprint out a U8 array called key array %d, which is going to equal, and then that, and we need I right there. And then what we need is the lexeme that we can pull from right here. And here we go. For lexeme size output %d comma, and I'll make that hex real quick, and then lexeme.string I, right? So there we go. Now I don't have to escape my strings. I can just output them like that. And you know what? It's like, it's not all that hard to get that right, but you have to put the percent sign in the right place. There we go. Cool. So we get key array 0, key array 2, key array 3, 4, 5, and so on, right? So these are the arrays of values that my key table needs to store. And, you know, that'll change every time I run it, because we're randomly generating these tables. And then what needs to happen is they get stuffed into these pointers here. Interesting thought. Anyway, I was just letting an idea run through my head. So if we look at this, like, does 76 have a length of 3? 1, 2, 3. Does 75 have a length of 5? 1, 2, 3, 4, 5. So it looks like this all checks out. This makes sense. The first one have a length of 8. Yeah. Alright, so the next goal is we have these tables. They contain the keys that we need to check against, and we have these tables that have the hashes. So now we have everything we would need to do a lookup. The last thing we would need is we need a table that contains the results in one spot. So for that to work out, what we're going to need is, first of all, the Lexem hash that we have down here. Where is that? Lexem. I thought it was called Lexem hash. There it is. So it's a part of a separate universe. It's going to not only be part of a separate universe with a function in it, but it's going to be part of a separate universe with a type in it. And this separate universe is the code that is handwritten that's a part of the handwritten code that's a part of the, what do you want to say, the runtime code, right? So we're generating all this runtime code, and the dang lights in my eyes really bad right now. We're generating all this runtime code, and the runtime code is mostly generated, but it's going to want to have a few pieces that are handwritten. So this is the code that is handwritten that will live with the runtime generated code eventually, and that doesn't really have a place to live yet. So Lexem hash is like that, because that needs to get called both in this code and in that code. Similarly, we have sort of like Lexem table value or something like that. And this contains a table, it contains a couple things. It contains the sub-kind of token that you want, as well as the table base, or token base kind that you want, right? So both of those get stored in there. Jeez, it's so bright. Okay. It's too bright. I can't get away from the light. Oh well. I'll just have to... Maybe I can raise my monitor. Might make my camera angle look weird, I'm not sure, but it's gonna work for now. Okay, at least it's not in my eyes as much. At least not in my natural angle. Oh, shoot, it still is. If I move the camera right there, that'll block the light. Then I can make some progress. Ah, it's still not quite right. There we go. Alright. So, the next step is the results table. So why am I generating each of these as a separate array? Well, it's kind of like when I'm doing the hash checking, I want to check the hashes in order, like from wherever I first go into the table, and I want to be able to check the next one over. So I'm kind of like just need to do a bunch of these in a row, and then once I find a hit, I'm going to do a check here. Now, a check here doesn't necessarily mean that I'm going to do a check out of the next table, right? But it also is totally possible that I want to do iterations over this table at some point in the future. So I kind of just feel like I want to have each of these be iterable concepts that don't necessarily always get iterated for their relationship to other things. So that's why it's three separate things rather than like merging this with the results or merging this with the hashes or something. It's the hashes because we can iterate hashes quickly, keys so that we can separate that out from here, and we can still iterate the key pointers separately at some point if we want to, and separately from the results is what I'm saying. So the final table is a table of Lexeme table values. So it's our value array. Same number of counts as before. If we don't have a slot there, then yeah, 0, 0, just like with the other one. If we do have a slot there, then what do we put in these spots? Well, something like this. The base kind needs to come from a direct value lookup, and the sub kind is going to be by a symbolic name. So what do I mean by that? Well, first of all, we have that slot, so I'm going to just grab that pointer for the first time instead of doing what I've done before and not grab it, because we're going to be referring to a couple things in there. So one thing we need is we need to be able to gen token full name. So that's going to come up here now, and char star full name equals full keyword token name or something like that, or full token name is good enough. So the way we get that is gen token full name. I need to pass it an arena. I believe my arena is called Scratch. Yeah. So I need to pass it a Scratch, and I need to pass it the keyword name. I think that's everything it needs. Yeah. And then that is how I fill in the second slot, full token name, right? So that's not so bad. I should probably throw that into a separate temp block. So just because we can avoid a little bit of extra buildup of memory right there. Not that that's going to make a big difference. One way or the other, that memory is getting freed. But I just like to take advantage of easy opportunities to throw in temporary memory blocks where I can to keep the memory usage smaller. So that's good, and then the other thing we need is that U value. Where is that coming from? That U value is going to be coming from, we need the token kind set, right? It has a name to putter lookup. So to do that part, what we have to do is, I think we have tokens. We need to use the name to putter. We need to do a table lookup on that table, looking for the name that you get from keyword name string, keyword name size, and really what I want to do is pull out the name right here, since we're using it in 3 places now. Then we can just do this, right? And so we do the table lookup. We can assert that we find a result, right? And then we grab the val. You've seen me do this before. We need to read out of my table type that contains a val, and then cast that to what's stored in that table is a token kind node. So this is token node equals token kind node int as putter val, right? So there's my token node. Now, why do I need the token node? Because it contains the base kind. And the base kind is what we want to stick in right here. So this right here was for getting the full name of the token from a base name. This right here lets me turn the base name into a token kind node, and a token kind node can give me the base kind value tied in with that particular token name. So given just this name, I'm able to derive all of the information I need from this table, right? And that's good because that's all the information I have available to me, but that was quite by design from how this whole thing was initially set up, that this would eventually work out, right? So that's cool. So now we have our key arrays. right here. And after our key arrays, we have our value arrays. And our value arrays tell us what base kind and what specific, like language specific kind of token that particular keyword is supposed to attach to, right? So when we put these things in, I keep seeing, and it makes me think, yeah, hash tables are tricky. So there's this interesting idea that occurred to me that if the last slot in a hash table was zeroed, you wouldn't actually need to store it. You would just need to lie about the size of it when you're going to do the modulo, but I wasn't sure if it was worth it. But then the idea also occurs to me that if you have two of these in a row, that it feels like you should be able to do something about that. But the answer to all of this is you can't, because the way these things lay out really matters, is really determined a lot by the hash function you choose and the modulo that's getting applied to it. So you can't just say like, oh, let's pull these all up by one, because there's no way to just say, let's adjust the function so that these numbers all come out one less and none of the other ones do, right? Or to say, let's make all of this layout the same way with a smaller modulo. It just doesn't, it's all kind of falls into place by chance the way it does, and so you can't do much to tweak the layout given the layout. The layout has to just work out, which is what makes hash table randomization make sense to me in the first place. But anyway, so a couple thoughts. All of these say 4. Why is that? That's because these are all keywords, and they all save their keyword. You can see right here literal true does something different, so there actually is a case, even in this table, where it does matter. My thinking on this was there might be languages, I mean take like Lua for instance, where you have to do things like opening and closing scopes via keywords, where it just would make sense to be able to do that, right? It just makes sense to be able to say, hey, we want to assign any type of base keyword to any of our keyword like results, so the base type isn't assumed. The base type can be anything. Plus in some of my other tables you'll see other numbers. So this table just says whatever you find, it's always a preprocessor directive. And I believe the final table will say that it's a 4. So, there's some flexibility in being able to say what type you are right there, rather than hard coding it as a fact about the whole table or as a fact about how keyword tables work in general or something for all keyword tables or anything like that, right? Hopefully that makes some sense, all these ideas. So we now have generated from our table layout the table we can actually use at runtime to do lookups. So our next goal is we need to clean this up a little bit. We've done a single pass over all these things, but there's a few problems. First of all, these names, key array 0, hash array, all these key array number things, key array itself, and value array are going to collide with all of the others. And since they're colliding, we're not done. We need to distinguish them. So how do we distinguish them? Well, I snuck in here, I didn't explain why, a pretty name when we started working on these tables. And the pretty name is for that purpose. So now we can come in here and just drop our pretty name at the beginning of each of these things. Pretty name, pretty name, pretty name, Boom. So now we have distinguished those names. Right? Only problem is here, we're still referring to the wrong thing, so we actually need to come in here and use our pretty name again. There we go. Sometimes the sound effects help to get, your brain learns associations between things. So if typing something with sound effects is easier for you, because you've practiced it that way so many times, you got to make the sound effects to actually pull it off sometimes. That's what's going on there, in case anyone's been wondering. So yeah, we have here main keys, key array. Down here we have pp directives, key array, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's pretty cool. It's pretty cool. I'm guessing that lays itself out differently every time, even though it seems to always be able to find a 15 pretty easily. It's, yeah, totally laid out differently though. so amusing to me. And the hashes are different for the same strings. So next, what we want to do is we want to next, I guess we want to is there anything else we need to do for these? I'm trying to think of any other issues with the table generation, but that might be it. We might have actually finished generating the tables, and we might need to switch back to how we look things up inside a table. If that's the case, I mean, that's good news. No complaints for me to be in that situation. Okay, so there is one more thing we need to generate, which is that for each of these tables, we need to tell someone what the seed was for that table, right? So U64 pretty name seed equals, and then I'll put in a little hex there, 016 LLX, new line, and then we need the seed. Now the seed should be stored on the table layout, right? So up here when we make one of these layout things, tell us what seed was used to generate U. Right? So then when we get a layout back from up here, we should be able to just take the layout key, layout seed, and stick it right there. What do we got wrong? Ah, you need the pretty name still. Okay, so now I should have my seed, and there we go. So what's kind of interesting about that is if you wanted to get the same table, all you have to do is lock down the seed and the size. So really all we have to do is we don't have to remember these whole tables. What we could do is just say, hey, when you go to generate this stuff, if you have a table that you've found in previous generations that work really well, just remember the size and the seed and give it back to the system, and it will do the same thing it did before. And you'll get back the same thing. You won't have to do any of the optimization work ever again. And this will stop changing every time you generate it. So that might be a cool thing to put in there at some point, the ability to lock in a particular seed and size for your table. PP directives, value array, PP directives seed. Because like this one, for instance, there's no reason for this to change every time. We just run it like 100 times and find one that gets the maximum single error down to a 1. Remember which one that is, and then stick its seed in permanently, right? Same thing with this one. This one, since it's always going to be a table of just one element, and nothing else, there's no point for its seed to even be anything at all. Its seed could just as well be 0 every time, and you'd get the same result. So we could avoid this and this randomly changing every time for no reason if we did that. So yeah, there might be some payoff to playing with that concept at some point, but again, for now, I'm just trying to get the very most basic feature set up and running with reasonable performance and the ability to be generic across multiple parsers, or multiple language lexers, without going too crazy on all this other stuff. So we'll leave that all for some other time. I'm just visually inspecting to make sure everything makes sense for a little while, because sometimes it's just the easiest way to find a bug is to 7, 8, 9, 10, 11, 12. So just double check things. 43. Yeah. Okay. So alright. My next move is going to be that I think it's time to handwrite the lookup code for this stuff. So yeah, generating the tables wasn't that hard, and we can just go ahead and switch over now to the next step of the process. I thought generating tables would be an entire episode, honestly. But it just wasn't, so let's move on. So this wants to return a, I think we called it a keyword result, and a keyword result, I'm going to call this a Lexeme table lookup. Right? Lexeme table lookup is going to contain the same things as this, a keyword result dot, let's call that a base kind just to make it match, and then it's got to have a B32 found match, and there we go. So there's our table our Lexeme table lookup, and we're just going to handwrite the function that does that. So Lexeme table lookup. How do we call Lexeme table lookup? Well, we need the following things. I need to know the pointers to the table. So the pointers to the table include, let me see the run result again. The pointers to the table include a U64 hashes array, hash array, a string const UA key array, a Lexeme table value array, and a seed. So that's how we define the table. That's everything that the table. That's everything that takes us to look things up in the table. And then we need a pointer and a size for that thing we're trying to look up. Then what we can do is we get the hash from the Lexeme hash function, which just takes that part there. We're going to take that hash and turn it into a comparison hash, which just means we take the hash and we OR in a 1. And then what we do is we search the hash array. I guess one thing we're going to need that we don't have here is the slot count, which really probably should actually get generated, right? So down here when I was generating everything else, I didn't think to generate the slot count. Let's generate the slot count. Out I32 pretty name slot count equals that. Okay, so give me the pretty name, give me the slot count. Slot count, there you go. So slot count way up here is there. Okay. I guess I could organize this like that. There we go. So come on, there we go. For I32I over the slot count, if hash array I equals the comparison hash, then what we want to do is say, okay, back up. Why did we start I at 0? That should be I32 first index equals the hash modulo the slot count, and then index should equal my first index. You are all excused. You are the index. Index plus equals 1 if index equals the slot count. You've seen me write this before. I'm just writing the thing that does the iteration logic. If the index ever gets back to the first index, then we break, right? And we didn't find what we were looking for. So table lookup result, return result. So I just had a thought, which is that that table with the which is perfectly packed is actually kind of bad news. You don't necessarily want your table to be perfectly packed like this, because even though you might have been able to get the total amount of error down for the number for your inserts, these tables do need to support the possibility that the person searching them doesn't have something that's in the table at all. And so having a couple of slots in there that are just 0 actually give you an early out, which maybe means I didn't quite think through how this optimization works. Because like, say I come in here and I have something that hashes to this, but it actually isn't in the table at all. then I'm going to check all these hashes only to find I don't match any of them and finally find a 0 here. If I had allowed a few more zeros to creep into the table, the lookups would have been much faster. So I think the optimization for table size was a bad call, and we need to revisit optimization in a minute to rebalance things a little bit. We want more zeros in there so that lookup speeds can be minimized. What we really kind of want to do is we measured how far off the maximum slot count, like the maximum error count is, if we consider at maximum error count from something that is in the table, right? So we say, hey, this thing's in the table, it should be right here, but it's actually right here, so it has a slot error count of 1, 2, 3. But what I really want to know is what is the largest run like this? Because large runs like that are trouble for anyone who is looking up something that's not in the table, since not finding a 0 for a long time means checking more things. On the other hand, all we're checking is a series of 64-bit values, and the chance that we find two 64-bit values that match when we aren't actually going to find a match is pretty low, so maybe it's okay, maybe that all those 64-bit checks are fine. But I don't know, I think we could just tune things a little bit more in favor of sticking in some zeros here and there, right? Without any trouble at all, really. We still want to minimize the errors for correct things, because whenever we do have a match in the table, we want that gives us, matches in the table will happen on pretty high rate, so we want the matches to come back quickly too, and minimizing the error for a single slot that is a match helps in that case. But it doesn't help at all in the case where you're not in the table, which is like more than half the time. What helps when you're not in the table at all is that there be lots of zeros to break up the search. Yeah, so we'll need to go back to that for sure. Okay. If the hash I'm looking at matches the hash I'm comparing with, then the next step is see if my keywords match, like if my lexeme matches. So if we'll just do string match by hand here, because we're already in sort of like we're already in a mode where we're kind of downshifted in speed a little bit from the rest of the Lexer because we've decided to do a table lookup. So doing the string match, we're going to match against the key array index. So now you'll see we're only pulling in a string on the occasion where this part matches. And then if that goes through, we confirm that we have a match. And we can say, okay, we found a match. And the result.base kind comes from the value array. So we only actually go to the value array once, and that's if we succeed on both of the previous two checks. And once we've done that, we can break because we found our result. On the other hand, if we're looking through the hash array, and the thing we're looking at is a 0, this is what I was just talking about before, so if the hash array is a 0, so we can check against our comparison hash. If that's no good, we check against 0. If we're a 0 in the hash array, then we can break, and that's because we know that there won't be a match once we see a 0, right? So let's just make sure that that's all going to check out. Very good. All right, let's do that. So let's return back to the optimize keyword layout function, and this part's fine. There's nothing wrong with that, but I want to look at this again. So this is actually doing keyword layout optimization. No, that's not the part I want to change. Yeah, so this is actually generating the keyword table. I want to temporarily switch off of generating the keyword tables and go back to looking at the debug print keyword table metrics. And that needs a key layout and a keywords.count, right? Good. So here's the thing, is I said I wanted to keep load factor close to 1 because that would mean that we weren't wasting space. But a little bit more space waste will mean much faster table lookups. So I'd actually probably want this to be closer to 0.5, honestly. Um, so a couple thoughts. If I'm gonna just go ahead and push that towards 0.5, then I'm gonna expect error score to be way, way smaller. Right? So we're going to have to retune these optimization metrics a little bit. Right, this part here that's doing the lightweight and the heavyweight optimization efforts needs to be quite different. So we're initially starting slot count like that. I'm going to start by saying let's put init slot count as an option up here. And so now all we have to do is say, look, I want you to start with double. Okay? And so let's take a look at how that goes down. So when you're filling out a slot of 132, you found the match exactly immediately, and then you spent a lot of time doing all this. Now, probably the reason it took longer to execute is that the process of filling out these tables has become more costly. But I want to see if, like, here, for instance, now we are pretty much never... So here's a question I have. Before I did that, yeah, it's a little faster. So the size of the table totally does change how long it takes you to fill that thing out, which is good to know. Surprised how long the hashing part takes, honestly. This here, so this used to be getting an error score of about 3, and now we can drop it all the way down to 0 by just increasing the load, or letting the load factor be a little bit larger. This one is a special case. We actually want to say that there's a special case if our keyword count is 1. So this is going to be something like, this maybe doesn't need to actually work like this. This probably is a universal concept. And what we're going to do is say if keywords.count is equal to 1, honestly, we probably just say, like, if it's not at least, like, 5 or more, then let it be as small as it can get, right? Because that'll just work out. But, like, here, now what's happening is it obviously immediately hits its target goal of, like, the error threshold, because it's, like, trivial now for it to meet that target. So, do I really need times 2? Not so sure I need times 2. Let's say that it's more like three halves. Let's just bisect. Alright, so now it's getting an error score of 13. Now we're getting, like, somewhat longer runs of non-nulls, right? Which isn't exactly what we want. So what we have to do is we have to turn up the heat when it comes to error score. We want the error score to go down. So you need to achieve an error score. Let's see, if you're starting off with that, you should at least be able to get 2/3 for free, but 2/3 would actually only take you down to 44. I bet you could get 1/3 as your threshold. There we go. So interestingly, you got exactly 1/3 when I did that. That seems unusual. But yeah, that is forcing you to actually grow the table a little bit more, but not by very much at all. And so that does mean that somewhere in that range, the threshold kicks in again and makes you do some work. And the goal of that would be to avoid long runs. So really what's kind of interesting is the way I actually should score these is very different now. So I'm going to change the error score computation completely. The current concept of error score is just not going to be very helpful. I'm going to call it an error score if I say, what if at this slot I looked something up that was not in the table? That's the error. So every slot that's null has an error of 0. You look something up that hashes to that spot, you get it done, you figure out the result in one comparison. If it is here, it's 1 error. This is 2 errors, so 1 error plus 2 is 3 error total, plus 3 more is 6. So we'll add up the range of consecutive non-nulls and basically take the triangle value of that. So 1 is 1, 2 is 3, 3 is 6, and so on, and add that to the error and see what kind of error values we're getting. I'll go ahead and loosen up the error threshold since I don't know how hard it's going to be to optimize from that perspective, but we're going to just totally change error score completely. So error score, max single error, you're not relevant anymore. Thanks for playing, but you're gone. Contributed error can also be removed, because this was more so optimizing for speedy lookups for things that are in the table, but I actually care more about speedy lookups for things that aren't in the table. So contributed error doesn't need to hang out anymore. Contributed error, contributed error, contributed error, contributed error. There we go. Okay, so all of our old concepts of error are gone. How are we going to do error scoring now? We're going to do it as a post pass after we've stored everything into the table. So what I want to do is for each slot in the table, if let's see. So I'm just storing slots and hashes. If the slot at I is equal to 0, then run length drops to 0, and we don't do anything to increment the score. Otherwise, what happens is the run length increments by 1, and then the layout.error score increments by run length, right? So if we are going along and we see we see a null, and that'll mean we're at 0. And then until we see a non-null, what'll happen is the run length is staying at 0, and then as soon as we see one non-null, the run length goes to 1, we add 1. The next thing we see has a 2. Actually, the way it actually is working is that I'm growing the triangle the wrong way. The first one shouldn't have had an error of 1, it should have had an error of however many things in a row there are about to be, but we don't know that yet. But one way or the other, I'm getting the triangle error in there. There's only one time when it gets the wrong result, and that's when it fails to understand the idea of wrapping around the back, front to back, right? So how do I account for that? So say I have 2 at the front and 2 at the back. I should have gotten the triangle number of 4, but I actually got the triangle number of 2 twice, right? So instead of getting 1 plus 2 plus 3 plus 4, I got 1 plus 2, 1 plus 2. So what I need to do is, when I get to the end of the array, I have a run length. I then want to do a sort of like wrap around section. So I'll do another 4i32i if it's less than slot count. And what's happening here is that everything I see, if I see a null, then I'm done. Right? The only point here is to add in the amount that was lost in the wrap around. If there's never a null, then what would happen is this error would just be astronomically big. And I guess if slot count was equal to the number of things we were trying to store, then in theory the error should always be n squared, where n is the number of slots, right? But I'm going to just ignore that case. I don't really know what I would do about that. I guess down here there's the weird situation where that actually does happen. but again, I'm not really sure. We gotta like specially optimize that small stuff in a slightly different way. For anything big, like the 66 or the 15, the way I want to think about it is if I got to the point where I had a run of 2 at the bottom, then when I come back around to the top and I see another one, I don't want to add in a full 3 because I've already added in 1 for that spot before. So really what's happening is I had a certain amount of run length that should have been accumulated onto that spot that wasn't, and that run length is 2, right? So the thing that really needs to happen is I just need to add in the run length without incrementing it, right? To put it another way, if I have like, here's this error, here's an error, a bunch of stuff happens, and at the very end, here's an error, then when I do this wraparound, what I'm doing is I'm saying I already have 2, so just come back around here and add 2 there, and then we're done. So now it'll treat this as if it's the tail of this, right? Does that make sense? Hopefully that makes sense. And I suppose that that'll do a roughly correct job of blowing things out of proportion, like just making gigantic errors if there is ever not a null anywhere in the table, but that should just never be the case except in these really small tables where I will want to think things through differently anyway. I might just want to say that this only happens for 1, because for 1 what would happen is we'd look at this, we'd get a score of 1, and then we'd look at this again and get a score of 2. And we could easily say that that's easily avoid that by doing this, right? And then you'll always just get an error of 1, which is the ideal error for that table, and it'll work. For a table of size 2 with 2 slots in it, you would be getting an error of 4. But that's not how it would get computed. It would get computed as 5 by this. This really only works if there are nulls in the table. So I guess what I have to say is this needs to, when it's doing this clamp bottom, it needs to make sure that the slot count is at least 1 bigger than that. And then this all works. Okay. So that's how I'm computing error now. So I guess contributed error is greater than... Yikes. Okay, so I probably shouldn't have taken out the contributed error stuff, because even though it's not a part of the layout, it is a part of the Robin Hooding that I want to keep. So, contributed error, slots, contributed error, U64 contributed error equals 0. Contributed error. So we still want that so that we can keep track of the Robin Hooding stuff. And there we go. So now our error score is turning out to be 66, and it has to make 651 slots to get there. I'm kind of curious why it has to make so many slots to get there. I'm also kind of curious how it made so many slots without pooping out. But shouldn't this have a total error of 66? Oh, it does. So this is how big the table had to get before it could space them out that far, which is bad. So 66 is now actually the minimum amount of error, right? This before the way we were measuring error, this number here was the smallest it could, was like the sort of a reasonable max to put on it. Now this is actually as small as it can ever be. The biggest it could ever be would be keywords squared. So we want something in between keywords and keywords squared. Maybe a fair thing would be to take keywords to the power of 3 over 2, you know? So that would be basically to do this. I32 times the square root of keywords count. So now it's giving me a table of size 99. So exactly a 2/3 load factor. So in other words, it took the initial slot count as correct, and it managed to find something right away with a error of only 149. So what I probably want to do is, we're going to have to spend another episode on this concept, but just to wrap things up for this episode, let's take a look at error like sort of like, I don't know what you want to call it, like error per lookup or something like that. And the error per lookup is the total error score divided by the slot count, because this here represents the what we got when we added up how many steps you'd have to take for each slot if you started looking at that slot for a string that doesn't appear in the table, right? So this has a score of 1, this has a score of 2, this has a score of 3, this has a score of 4. All of that got added together, but what we want to do is say, what happens if that amount of error gets distributed amongst all of these, because each of these has an equal amount of chance. So the worst error is a 4. That could happen, and I should turn this into a 4 if we want to do this correctly, but on average, it would be the sum of all the different individual errors divided by the number of slots, right? That would give us a more meaningful appreciation for how much error is happening. So right now, it's about 1.5 with this table. So I did the square root thing. Let's just say we're going to go bigger than that. So let's say the acceptable error threshold has to be smaller than that. Instead, it needs to be no more than double this. Right, so now my error per lookup is less than 1. But I still have situations where that lookup error is 1, 2, 3, 4, 5. So I want to get that working. And maybe we want to optimize on this more so than this. We'll see. My tables now are a lot bigger. I guess that's something we'll have to trade off on, like, do we really want that? We might also want to find a way to avoid having long ranges of nulls. The other question, I guess, is have we adjusted this? Because, like, that's obviously not valid anymore, but what happens when we try to run heavy optimization on this? Does it do too much work? Does it do a good job? Does it find something really good? So it found a table of only 114 with an error per lookup of 1.1, which is pretty good. We still need to know how well this is turning out, but it's doing a pretty good job at that, actually. Kind of spreading the table out. This here got a slot count of only 22, so it didn't grow by that much. And really nice low error per lookup. Okay, so this has been us working on generating the layout text, the table code, and then switching back to optimizing with a new insight in mind. So next episode we're going to wrap up the optimizations we just have started looking into, and then we're going to finish the emit stuff completely, probably. Alright, so see you around for the next episode. Later.